Hi, and welcome to a third installment of Dr. Jed's calculus videos. We're going to do section 3.2 again from Rogowski. This is part 2. It's the stuff we didn't cover before. Well, most of it. Our goal is to talk about how the graph of y equals f of x and the graph of y equals f prime of x are similar and different. So the things you need to know, since we're talking about graphs, you better be good at graphing. You should have an understanding now of continuity, how it relates to limits, what it means, and also, of course, the definition of the derivative. You better know that because that's what we're talking about. Now, what is the relationship between continuity and differentiability, which means to have a derivative? So let's just take a quick look. If a function has a derivative at a certain point, it must be continuous there. I don't want to get into the formal proof of this, but take a look. Here's the definition of the derivative. If this exists, that means this limit exists. Now look at the bottom. The bottom goes to 0. If the bottom goes to 0, the top better go to 0. So first off, f of a better exist. If it doesn't, this doesn't make sense. Because it doesn't make sense without that being there. And the second thing, this better get close to here. If this goes to 0 and this doesn't, the limit doesn't exist. So since this does go to 0, this better go to 0. Hence, f of x better go to f of a, which means the function is continuous. Now, you might think, well, that means they're the same thing, but they're not. It is possible, if the function is continuous, that the derivative does not exist. The way I've written this is if f of x is continuous, f prime of a might exist. It might, but it's not guaranteed. These are not the same thing. Continuity does not imply differentiability. Differentiability does imply continuity. So let's take a look at some examples. Here, the derivative exists. Here's the curve, and you just find the derivative. The derivative, recall, is the slope of the tangent line, and it works really well there. But other things can happen. How about this example? This looks very much like a function you should know. Boink, boink. And right down there, what's the slope? That's the problem. The slope doesn't exist. It does for here, it does for there, but right at the bottom, it wobbles because of that angle. The derivative at that point does not exist because there's an angle. And another reasonably classic example, this one, the function is perfectly nice, it's continuous. But right there, the slope becomes infinite, a vertical tangent slope. So the derivative at that point doesn't exist. So when you're looking at derivatives, there are three options. One is the derivative might exist. The second is the derivative doesn't exist because of the angle. And the third is the derivative doesn't exist because of a vertical tangent line. Now, what about the continuity of the derivative? That's more complicated. If the function has a derivative, the function is continuous. But does that mean the derivative is continuous? And the answer actually is no. It is possible to create a function which is continuous and has a derivative, but the derivative itself is not continuous. It's messy. It's not really helpful to think about it. There is an interesting property. It has an intermediate value property, sort of like the intermediate value theorem, that from here to here, you can get everything in between, but it's not necessarily continuous. We won't think about that because we like functions that behave well. Let's take a look at one that does behave well and see if we can look and see how the derivative is related to the function itself. Here's a graph of a function f of x, y equals f of x. How would we go about finding, a graph of the derivative? So, you start by thinking about the pieces that make the most sense. What is the derivative? It's the slope. So let's go until we find something useful. Slope here is negative. It's going down. Till we get down there, oh, what happens right here? Right here, if you look at that, the slope is horizontal, which means the number for the slope is 0. That's the derivative, right? So the derivative right here, for this function, the derivative is 0 right there. Now let's keep going. It goes up. Now, right about here, the slope is 0 again. If the slope's 0 there it is. The slope is 0. And if you keep going, we'll find the slope is positive, now it's 0. Right to here, the slope is 0. Now, this is not one of those weird functions where the derivative is going to fail to be continuous. The derivative will be fine, it'll be continuous, so we have to connect the dots in the right way. How high does it go? Well, the scales are different. The slope has units of rise over run, whereas the function has units of run. They're not the same. If you go unitless, you can graph them on the same thing, and it's useful to have a feel for it. But scale is going to be kind of an odd thing. Without tick marks, I can't tell how tall it gets, so I'm estimating. How steep does it get? Well, this is the steepest down it gets for a while. Then it gets less steep, less steep. So the slope is negative here, and it's less negative and less negative. So it's coming up here. That's pretty much a line, so it's going to be something like this. Now what about here? All positive, all positive, all positive till we get to here. Those are positive slopes. Where are they steepest? It's steep here, then it comes back to 0 steepness. Then it goes steep. Is that about, those are about the same steepness, that's a little less. So it looks like to me, right about here is as steep as it ever gets. I'm going to say that's as steep as it gets. And it comes back to 0. But it comes back up slowly till about steepness there. To maybe about that, and then comes back down. Notice, I don't think that's quite as steep as that is. You might disagree. If you do, maybe that one's a little higher. But we're sketching. We're not trying to make a perfect graph right now. We're just estimating. And then this, compare that with this. This to me is steeper. In fact, actually, now that I think about it, that's steeper than, well, it's about the same steepness. Maybe this should go down a little bit more, now that we're trying to get a good estimate. And this is not as steep, so it's probably a little bit less. And it kind of stabilizes into a line. If it's a line, the slope stays constant. So the derivative gets to more constant. So we get something kind of like this as y is f prime of x. Now, what do? The other way around. The other way around is harder. So if this one didn't make a lot of sense, that's an arrow by the way. So is that. If this one didn't make sense, work on this one for a while until it makes more sense. But the one that we're going to do next is the other way around. Here's a graph of the derivative. Can we now make any sense, heads or tails, of what the original function is? Well, we have an issue. These are slopes, but without a starting point, we can't make headway. So I'm going to give us a starting point. It could be any starting point, but I'm going to use 0, 0 because, why? Because it's a good starting point. I like it. So, the slope is here. Now what is the slope again? The slope is how steep is the graph? It's positive. Not only the slope of f prime. I mean, f prime is the slope, and then f prime is positive here, so the graph's going up. It's going up at a sort of a constant clip throughout here. Going up, and in backwards notation, that'd be going up also, right? Now, what happens here? The derivative is dipping. Does that mean the graph dips? It actually does not mean that. It means, since the derivative is the slope, we have less slope. It's not going up as steeply. And then it picks up again. So it's not as steep anymore. But then it picks up again and gets steeper still, right? This is the steepest it ever got. It's the max for f prime. That means that's a steep, since f prime is the slope. That's the highest the slope ever gets. That's the steepest it ever gets. And then when the derivative gets to 0 here, that turns out to be a maximum for the graph, because the graph was going up while the derivative was positive. Now the derivative is negative, which means the slope is negative, which means it's going down. And it's going down steeper and steeper. How about the other side? Well, it's still going up. This, before it, the derivative is negative, which means the slopes are negative. That's negative slopes. Afterwards, the slope is positive. That's positive slopes. We're going to have a minimum right here. Something like this. I'm sorry, I said that wrong. That's not a minimum, is it? You've been reading ahead and you know that's wrong. This is, just like this one was, the steepest it ever got. This is the steepest. No, yeah, it's all right, because now the slope's negative. I was right the first time. See, even math teachers can sometimes be wrong. So that's the lowest it ever got. Now over here, what's this? See, it's confusing, isn't it? But what is this? This is f prime. F prime is a slope. The slopes are negative here. It doesn't matter which way it's going. It doesn't matter how much, how steeply so much. It's negative. It's below the x-axis. If it's below the x-axis, That means we're negative. We're going like this. So, that is our rough drawing of y equals f of x. And that's our lesson for today. I hope it made sense. I hope you could see some parts of this are simpler, and some parts you really have to think about. Because if you don't think about it, you go too fast, you can get lost. Till next time.